Example 1. Find the linear approximation of f of x equals square root of x at the point x equals 9 and use the approximation to estimate the square root of 9.1. Our first task in this is to notice, based on our definition we have, what the linear approximation. It's a linear function that uses the slope of the instantaneous rate of change, the slope of the tangent line at our point, in our case 9, as the slope of our linear function. And another thing is, this function is only going to be valid close to that point, in our case close to 9. Well, L of x is equal to f of 9 plus f prime of 9 times x minus 9. That is the function. So we need to find each of those pieces. Well, first off, we know that the derivative of f of x is going to be 1 over 2 root x based on our power rule, which means that f prime of 9 is going to be equal to 1 over 6 because the square root of 9 is 3. That is worth pointing out. We're going to need that. Okay, so this is all scratch work. So L of x is equal to f of 9. Well, that's the square root of 9, so 3 plus 1/6 times x minus 9. I'm going to restructure that to be 1/6 x plus 3 over 2. So 1/6 of 9, of negative 9, and then adding 3 to that. So there is our linear approximation, or our linearization. Now we can find then linear approximation of 9.1, and I can't actually, well actually I can, this one is a repeating decimal, 3.016 repeating. That is the value of our linear approximation at 9.1. Now to test that out, we can actually find the square root of 9.1 and see how close this is. Now this I will have to round. This is 3.016620626, and it continues. It is irrational. And as you can see, that value is very, very close. Okay, at least up to 5 decimal places, or 4 decimal places, it's the same. Again, I will say these are only valid when you are close to the original point, the value of a. Okay, and here our value a was 9, and 9.1 is pretty close. So therefore, this is reliable. Now, example 2, find the linear approximation of f of x equals sine of x at x equals pi thirds, and use it to approximate sine of 62 degrees. Well, that first question that I need to ask is, before I even touch this, is can I use it to approximate sine of 62 degrees? Well, 62 degrees is actually fairly close. That's 60 degrees would be pi thirds. So that's fairly close. So this may, in fact, be valid. And because I'm going to need to do this in radians, because pi thirds is in radians, I want to convert this. And 62 degrees, use our conversion factor from 1.3. That is equal to 31/90ths pi. So that's the value we're going to use when we actually approximate this. Alright, now on to actual linearization. F prime of x, that is cosine x. So f prime at pi thirds is cosine of pi thirds, which is 1/2. And our original function, sine of pi thirds, is root 3 over 2. All that is information we need to write our linearization. Remember, that's going to be f of a. Right, f of a plus f prime of a times x minus a. Now, because because we've already found all that information, that is root 3 over 2 plus 1/2 times x minus 5/3. Now I may just leave it like that. I'm not going to rearrange that because that's not going to combine very nicely. All right, our linearization at 31/90 pi is approximately 0.883478, and it continues. So that is our approximation. Now, just because I can, I want to compare these two. Sine of 31/90 pi is 0.882947, and it continues. So that is, in fact, pretty close, well, to 2 decimal places. So for our intents and purposes, that's just fine. Could be better, of course. Last question for this. Example 3, find the linear approximation of f of x equals 1 plus x quantity to the n at x equals 0. And then use this to approximate or estimate 1.01 to the third. Well, first off, by definition, our linearization is going to be equal to f of a plus f prime of a and x minus a. Alright, now at the point 0, f of 0 is 1 plus 0 to the n, which is 1 to the n, which is just 1. So f of 0 is 1. Now for f prime of 0, well, let's find f prime of x first. By our power rule, that would be n times 1 plus x to the n minus 1. So evaluating that at 0, that is actually n, because we have 1 plus 0, so 1 to any power is 1 times n. And there is the information we need. Okay, so L of x equals 1 plus the derivative, that's n, times x minus 0. So that is nx plus 1. I'm just going to write that in slope-intercept form. Okay, we'll use that. Now we want to estimate 1.01 to the third power. So that means that n is 3 and our x is 0.01. So L of 1.01, well, it's L of 0.01 is going to be 3 times 0.01 plus 1, which is equal to 1.03. That is our approximation. Now, just to be, I want to compare these two. 1.01 cubed is, and this one is approximate, 1.030301. Actually, it's not approximate. That is equal. So, as you can see, to 2 decimal places, that's a pretty good approximation because 1.01 is, in fact, pretty close to, well, 0.01 is pretty close to 0.